This is a lesson on modeling and regression with rational functions in a pre-calculus course. I've covered modeling with functions in many lessons. We started with linear functions and we did quadratic and we've done polynomial and just general functions, right? Always, and this will go on my headstone for my grave, words mean things. Right? Words mean things. And so when you're reading problem statements, look for key words and phrases that have mathematical implications. I recently gave an exam with the word best in it, and you may see that as like a maximum, right? Best, maximum, you're finding a vertex, you're finding a turning point, right? So key words and phrases, word mean things, and they have mathematical implications. Always use meaningful symbols. So if you're given a speed, you may use S for speed, or velocity. If you're given a time, use T. I know you like to use X and Y. I know. But as you mature in your mathematical and scientific career, symbols have meanings. Give it some meaning. Make it mean something. When we're looking at the form of our models, with rational functions, we're just going to assume some simple model unless we're specified otherwise. It may say, oh, here's the model. Some problems just do that. They'll say, the model goes by a over x plus some initial value or something like that, right? And it would designate, it would tell you the form. If that's not given, assume a simple rational model. Assume a simple power, a -1 power, a -2 power. It may be a -3rd, but a -3rd could easily be modeled by a -1 power, okay? We're going to use algebra to solve. We're going to look for important points. We're going to use function notation where appropriate. And we are always at risk for losing points for not showing full mastery is verify your algebraic solution with a graph. Always check those answers on a graph. I want to see your graphs, okay? Not just the algebra and not just the graph, both of them together. I chose this problem because a lot of students have trouble with this one. I think it's because it requires an exact answer, and then they have trouble parsing that problem statement. There's just one sentence there, and you have to get a whole equation to set up in order to solve it. So it says a positive real number. All right. X is my positive real number. I'll just let it equal X. And this is a positive real number. X, it says X is, so let me write that out. X is means equal sign. Exactly 12 greater than its own reciprocal. So I'm going to write down its reciprocal, 1 over X, and then 12 greater than that. So I'll put a plus 12 on the end. One issue I see students have is they'll put a 12 here, 12 over x, 12 times 1 over x. And if it were the case, it would say exactly 12 times greater than its own reciprocal. But it says 12 greater than. So I'm going to interpret that as plus 12. This is 12 greater than its reciprocal. Find all such positive numbers. Okay, so I just need to solve. I'm going to multiply all the terms in here by x in order to get rid of that denominator. X. So I get x squared equals 1 plus 12x. I'm going to keep my squared term positive, so I'm going to move these terms over and let it equal 0. So I get x squared minus 12x minus 1 equals 0. Now that I have the quadratic form here, I don't think there's factoring. I can't factor, so I'm forced to kind of use the quadratic formula. So I'm going to say I have 12 plus or minus the square root of 12 squared minus 4 times 1 times -1 over 2 times 1, right? So if I simplify that, I get 12 plus or minus the square root of 144 plus 4, which is the square root of 148. Do you all see that? This is 144. And then I have minus 4 times -1, which is a positive 4. So 48 divided by 2. I'm going to take that 6 plus or minus 148. You can do this with your calculator. That's 4 times 37. Okay, so I have the square root of 4 times the square root of 37. So I get a factor of 2 square root of 37. I still have a 2 underneath there, so that's the square root of 37. I cannot approximate that. It says up here it wants an exact answer, so I'm going to leave that root 37 intact. That's how it's going to be an exact answer. I have two solutions here, so I need to remember what I'm looking for. I'm looking for a positive solution. The square root of 37 is a little bit greater than 6. So if I take 6 minus the square root of 37, that's going to give me a negative answer. So I am going to have to take the positive of this. So that is going to be my solution for this problem. So we can check our answer on a graph. I know you're dying to see this on a graph. Let me pull the graph up here. I generated it earlier for us. So here's this graph. And I don't want you to just graph the inequality. I want you to graph these two functions that you set equal, right? Our original number, f of x, and then another function, our other function, I'm just going to call it g of x. It's saying this original function, x, which is this red line. This is f of x. Sorry, you can't even see that. This is f of x, okay? That line, where does that line equal this function here? Well, I know the equation of that function here. That's 1 over x plus 12. You can see that it's the reciprocal function, and it is moved up by 12 units, right? 12 units upward. So I see two solutions. That's what I solved for. I solved for two solutions, definitely. I rejected this lower one because it was a negative one, and so I got 6 plus the square root of 37. The square root of 37 is approximately 6.1 something, right? So I get 12.1. That's where 12.1 is. Okay, so my answer checks out on this one. I have another example here that I know students struggle with, and I think it's a problem I may have done before in the problems in the lessons, but I wanted to cover this again. I think what students again have trouble with is just setting up the equation. Set up equation. You may be good to go once you set up the equation, but it may be hard to parse this information into an expression to be solved. All right, so I'm definitely going to set up a real quick physical sketch here. This is different than graph. This is a sketch, right? And let's say I have my river, and the river is flowing at some, you can call it a speed, you can call it R. I'm a physicist. I call it a velocity, like the velocity of the river, or the velocity of the water. I'll call it the velocity of the water. Bob can row 12 miles per hour in still water. Okay, so we have a velocity of Bob given to us, 12 miles per hour. Good for him. That's a pretty impressive speed to me, at least. We have some current going on. The total time to travel downstream and return upstream to the starting point is 2 hours and 40 minutes. Okay, so T total I'm going to have is 2 and 40/60ths. I want it as a decimal. And I converted that even to like a rational number, 8/3, right? 2 and 2/3 is 8/3. So he goes down and back in the river. If the total distance downstream and back is 30 miles. So to me, it seems like going down the river in this direction is going to be 15 miles, and then going back up the river is going to be another 15 miles. All right, those should be 15 miles, the same length. Okay, in one direction, he's getting help with the river. So Bob's going to have his velocity pointing in this direction, and so he's getting help from the river. But when he goes back up the river, he's got his velocity pointing in the opposite direction, and he's going to end up with losing some speed. Okay, so we don't know the velocity of the water. I'm just going to call it VW. So what I am going to put together is an equation for time, because I have a value for time, and I'm just going to let that be like my output value, total time. So if I need to find an expression of total time in terms of the velocity of this water, how much time does it take in regard with respect to this unknown variable, right? The velocity of the water. So what I need to remember is we know how to find velocity, right? Velocity is a distance divided by the time. And if I do just a quick step of algebra on here, I can say time is distance divided by velocity. And when I look at the total time, there's going to be a time to go downstream, and then there's going to be a time to go upstream. So that means I'm going to take the distance downstream and divide by the velocity downstream, which I know is the velocity of the bob plus the velocity of the water. And then I'm going to add on, that's the time down, and then I have to add on the time back. So that's going to be the distance upstream, the velocity of the bob minus the velocity of the water, because he's going against the water, right? So when I put all that together, I know I'm going to have a 15 here over 12 plus the velocity of the water, right? 15 miles. His speed is 12, and we don't know the water. And then we're going to have plus 15, 12 minus the velocity of the water. Okay, so that's going to be, those are basically my two functions. If I were to graph these, I would graph these two things. With the x variable, this would be the x variable. That's my input variable, and this is the output variable. What we're going to do is say 8/3 equals our total time expression. 15 over 12 plus VW plus 15, 12 minus the velocity of the water. I need to simplify this, and I'm going to erase this so that I can simplify it. We need to get a common denominator, and what you're going to notice is the common denominator is 12 plus the velocity of the water times 12 minus the velocity of the water, and that denominator there. So this term, this first term, needs a minus, a 12 minus velocity of the water, and then this term needs a 12 plus velocity of the water. So that's what's going to come out here. I have a 12 minus the velocity of the water plus 15 times 12 plus the velocity of the water. And then that gives me a common denominator. Okay, I'm going to keep simplifying. 8/3 equals, actually I'm going to bring over this stuff. I'm going to multiply both sides by that, and I'm going to notice that it's 12 squared minus the velocity of the water squared. And that has to equal 15 times 12 minus 15, the velocity of the water, plus 15 times 12 minus 15 times 12 minus 15, the velocity of the water. That cancels there with this term. Do they cancel? They should cancel. Yeah, this is a plus here. This cancels with this term, and we get 2 times 15 times 12, whatever that is. 30 times 12. I'm just going to leave it like this. Okay, so let me add another slide in here so that I can do a little bit more math. New slide. I can put a new slide in here. And I am going to change its layout to just be blank. There we go. So on the previous slide, this is what I had for my equation. I had 8/3, 144 minus the velocity of the water squared equals 30 times 12. That's what it simplified down to. I'm going to move the 8/3 over to this other side. I know it's tempting to distribute it, but if I move that fraction over the other side, I'm going to keep less terms and less fractions overall. So then I get this 33/8, right? Multiply both sides times 3/8. That cancels, and I get, let's see, that is a 4 and a 3. I get 30 times 12 again. That's weird. Did I get that right? Oh, I know why, because I need to do this. 12, if I divide by 2, if I divide by 4, 3 halves, right? Okay, 30 times 9 over 2, which is 15 times 9, which is what, 135? I think that's 135. Yeah, I can check my answers. 135, yep. So 135, 144 minus VW squared equals 135. I'm going to move this over to this side, this over to this side. VW squared equals 144 minus 135, which is 9. So the velocity of the water has to equal plus or minus 3. right? There's two solutions here. If I take a square root everywhere, when I take a square root, I'd have to consider two solutions, especially if I'm graphing, right? Especially if I'm graphing, when I look at that, I have a parabola and it's intersected at 2 points, right? So, but I know it's the velocity of the water, and I defined it to be positive, so I'm going to say that the velocity of the water is 3 miles per hour. That's going to be my algebraic solution. I know you're dying to see this graphical solution, and I'm going to show you what I'm going to move slides here. I'm going to show you what I entered into Desmos as my functions. It was the same things that I said before. I have 15 over 12 minus x plus 15 over 12 plus x. That's going to be this red function over here. And it's doing some weird things, which I'm okay with, but that was the total time function. This is a total time function. All right, and that's that red line in here. I set it equal to 8/3, which is going to be this blue line. Do you see this blue line here? That's what that blue line is. All right, and you can see that it intersects at my two values, plus 3 and minus 3, and I'm going to just keep my positive value there. So I verified my solution on a graph. I think I see students just like put in any random things and then get in a graph that like just verifies their solution, but this is the graph that I'm looking for. I want one function and another function, and I want you to show me where the points are that they intersect. I don't want to see just like a vertical line. The vertical line is the answer, but it's not representative of the original functions that you solved in order to get that answer. I know it can be a little tricky as you're learning, but I just wanted to be clear about what you're solving for. Another problem I have here is just setting up the large room one. To me, this is very similar to the river problem. It says Trinidad can paint a large room in 14 hours. Miranda can paint a room, the same room, in 84 hours. How long would it take the two of them to paint the room together? So the speed of one is one room in 14 hours. One room, 14 hours. The speed 2 is one room in 84 hours. Okay, Miranda, I don't know what you're doing. You got lots of music going on there, something like that. Taking her a while to complete that room, 84 hours. So when we're looking at this, we want to find S total. And so what we're going to do is going to take the speed of the one and the speed of the other and add them together. And so they say the one room will take how many hours? We don't know x. All right, how many hours? You could call it a t. I suppose you could call it a t if you wanted to. T equals, I don't know. One room in how many hours has to equal 1 over 14 plus 1 over 84. I think it's pretty simple to solve this. You can't just take 14 and 84. It should take less time, not more time. So make sure when you're solving this equation, you use good algebra. Okay, good algebra. And when I look at the graph of this, what I'm going to assume is that I'm going to take the inverse function, which looks like this. Of course, there's a positive and a negative, a first quarter and a third quarter of this function. And I'm going to let it equal just some value. Right? These two numbers added together is some value. It'll come out as a line across the graph, and you'll be solving for this intersection point, whatever that intersection point is. You can solve from here, but I just wanted to help you set up that problem. The last thing I have to talk to you about in this lesson today is regression. Regression with any kind of function. We've been doing regression with linear functions and quadratic functions and polynomial functions. We're on to rational functions. We're going to keep doing regression. So always graph your data. That's what you're learning in this class. Always graph your data. Notice if it's linear or nonlinear. And if it's nonlinear, what type of model is going to fit best? Is it going to be a polynomial function? Is it going to be a rational function? Is it going to be a non-power function like e to the x or a logarithmic function, right? We're going to get to those later in the course, but you should be identifying immediately whether this is linear or nonlinear. I give a problem in the lesson for this that has only 2 data points, and it would seem like maybe a linear function with a negative slope would work, but it may be told to you. You may be told use X sort of model, and then you can use 2 points. Any model can be defined by 2 points as long as you have the general form of that model. So we're using the accurate form of the model. We're using some sort of statistical program that we can graph and get that regression equation out. We're going to report it in proper function notation, and we're going to include our correlation coefficient, or our R squared. All right. Linear functions have an R, but when we get into powers and weird sorts of functions, non-powers, we're going to report that R squared. Tell me how well that data fit that line. All right. What I have for you is that 2-point problem. It says you built a small toy catapult. At first you launch a 16-ounce ball and it only goes 3 feet. When you shoot a lighter ball, it goes farther. So those are our 2 points, and you can see I graphed it on here. I have what? This should be, this looks like, 10, this is the second point, 10, 6, and this is 16, 3. Those are our 2 points. Again, it looks like it could be a linear relationship, but it says assume. Do you see where it says assume there? That's giving you words mean things, key terms. Assume that the distance and the weight are inversely proportional in some way. That could be modeled by a power function. Okay, that's kind of vague. My tip is to just start with the simplest inverse proportional. We're going to have a times 1 over x to the first power. I'm going to go easy, guys. I'm just going to go easy. It could be a squared. I'm not saying it couldn't be a squared. And what would tell me, do you all know what would tell me what function would be better, 1 over x or 1 over x squared? When I do these 2 regression models, I would have a correlation factor here, an R squared, and I would choose the R squared that fits best, right? The higher the R squared, the better. So whichever one has the higher R squared is going to be the best model. So I think even though it's not clear here, I'm going to start with the simplest models. I'm going to try both of those and see what it says. All right, so that's what I did. I'm going to get my mouse out here so I can show you some pictures. The model that I always go with, the easiest model too. If I can choose an x to the first power over an x squared, that's what I'm going to choose too. All right, so which one did I do first? Let's see. I'm going to bring this to the front and see which one it is. I forget which one I put where. All right, so this is a squared model. You can see that it's squared. It goes up in the same direction alongside that asymptote. So that's that squared power. And it gives me an R squared. So if I wrote out this function, I'll write it down here in this color. F of x equals a 622.2 1 over x squared. That's the model I used. Do you all see that? That's the model I used. And it gives me an R squared equals 0.917. Okay, so I'm going to keep that model in mind. Seems like it fits pretty good. 92% of the variation in the data is accounted for by that model. Let's get the other model out. This one's simpler. This is the simpler model. Maybe the simpler model worked best. I'm going to get this simple model out. You can see it's x to the first power in that denominator there. Right, you see that here. I'm going to highlight it, circle it in red. A over just x. All right, so I would say that function is 56.63 over x. That's it. All right, maybe I could write it in the same form, 56.61 over x. I'm going to note it's r squared equals 91%. I was writing the 91, 0.910. So I'm not going to lie, pals. The squared, the inverse squared, has a better R squared here. Do you see that? But it's not much better. It's not much better. 0.917 versus 0.91. If it were me, I would do this function here. That's what I would do. All right. But I think if you were asked proper, like just choose the best correlation coefficient, that would give this one. The problem specifically asks, use the regression to predict how far the catapult could throw a 1.62 ounce golf ball. So you're going to plug 1.62 in here. 1.62, 1.62. And I have a feeling that when you do that, both of those equations are going to give approximately the same distance. You may see, like, I would use the easiest, simplest one. And if that one wasn't accurate, I would go with the more precise one. But this is what we call parsimony. If you've ever heard this term in like scientific theories, we always go with parsimonious, the most parsimonious answer, which means the simplest. We're not going to make things complicated. So hopefully that helps you solve that problem with a little bit of efficiency.